Welcome to The Explainer. Today, we're talking about something that's changing, well, pretty much everything around us, from the medicine you might take to the chair you could be sitting on. It's called green chemistry, and it's basically a blueprint for a better planet.
But to really get why this is so important, let's just start with a question. Think about it. Those life-saving medicines we all rely on, just how much waste do you think gets made to produce, say, a single kilogram of a complex drug?
All right, get ready for this because the answer is pretty shocking. In some cases, we're talking about 100 kilograms of waste for every single kilogram of medicine. Yeah, you heard that right. 100 to 1. Just try to picture that. For the medicine that fits in your hand, there's a pile of waste 100 times its weight somewhere. That's the hidden cost of the way we've been doing things.
And that huge number really gets to the heart of the problem, doesn't it? It's what some people call chemistry's dirty little secret. The hidden environmental cost of our modern world.
You see, for a long, long time, chemistry was really just about one thing. Can we make the molecule? That was the whole game. And if the answer was yes, how we got there didn't matter so much. This led to these really intensive, complicated processes that, surprise, surprise, created tons of nasty byproducts. It wasn't just a mistake. It was kind of built into the system. Okay, so what if we could just scrap that old playbook? What if we could design chemistry to be clean and efficient right from the very beginning? Well, that's exactly what we're going to talk about. It's a whole new blueprint, a total rethink of how chemistry works, starting with the atoms themselves. This whole idea was really championed by two guys, Paul Anastas and John Warner, back in the 90s. And the core concept is actually super simple, but it's also revolutionary. Think about it. Instead of making a huge mess and then trying to figure out how to clean it up, green chemistry says, hey, how about we just don't make the mess in the first place? It's about designing out the bad stuff from the get-go. Totally proactive, not reactive.
And to make this idea something people could actually use, Anastas and Warner came up with a list of 12 principles. You can think of it like a new rule book for chemists, a guide for doing things sustainably. It covers the whole shebang, from preventing waste and using safer materials to saving energy and, just being safer in general. All right, let's zoom in on one of the big ones. It's called atom economy. Now stay with me here. Imagine you're baking a cake, right? Atom economy would be like making sure every last bit of flour, sugar, and egg you started with actually ends up in the cake. No wasted batter, no stuff left in the bowl. That's what it is for chemistry. Designing reactions so that all the atoms you start with end up in the thing you're trying to make. It is the absolute peak of efficiency.
Okay, so we've covered the what and the why. But how do chemists actually do this stuff? Well, they've got a whole new toolkit with some really cool strategies that are changing how reactions are done. So, one of the biggest changes is moving away from what's called batch processing to continuous flow. The old way, batch, is kind of like making chili in a giant pot. You just dump everything in, give it a stir, and hope it turns out right. The new way, continuous flow, is totally different. It's more like a super precise assembly line, where tiny amounts of your ingredients are constantly pumped through these little tubes.
And here you can really see the difference. On one side, you have the big old glass flask. It's clunky, hard to control. Then you have flow chemistry, with its network of tiny tubes and pumps. Because you're working on such a small scale, you have amazing control over everything. Temperature, pressure, how things mix. And what does that mean? It means your reactions are safer, way faster, and a whole lot more efficient. And the results? I mean, they're just mind-blowing. Look at this example. A specific reaction that used to take 3 hours in a batch process now takes 30 seconds in a flow system. Let me say that again. 3 hours down to 30 seconds. Plus, it used half the catalyst to get pretty much the same outcome. That's not just a little better. That's a gigantic leap forward. That's the power we're talking about.
But okay, flow chemistry is just one part of the picture. The green toolkit is packed with other cool stuff. There's catalysis, which is all about using special substances to make reactions go faster. Then there's biocatalysis, which is super cool. It's basically borrowing enzymes, nature's own catalysts, to do the work for us. You've also got using renewable stuff, like plants instead of fossil fuels as your starting materials. And finally, just switching to safer solvents, like water. Each one of these is a huge step in the right direction.
Now, I know what you might be thinking. This all sounds great in a lab, but does it actually show up in the real world? Well, let's get to the proof, because this stuff is already all around you. Seriously, you'd be surprised how much green chemistry is already part of your life. Let's circle back to medicine. Take Viagra. Pfizer totally redesigned how they make it, and in the process, they cut hazardous waste by more than 80%. That's huge. Or what about a simple painkiller like ibuprofen? The original way to make it was, frankly, a mess. Super inefficient. Now there's a new, much greener process that has way better atom economy, so less of the ingredients go to waste. It's literally in your house. That IKEA furniture? They swapped out the old formaldehyde-based glues for safer ones made from plants. That's way better for the air you're breathing at home. And you know PVC products like vinyl flooring or electrical cables? Dow has developed plasticizers from biosources, making those everyday items less toxic. And it doesn't stop there. Think about high-tech materials. DuPont is using engineered microbes and corn sugar to make a key ingredient for polymers, and that process cuts greenhouse gases by over 40%. And your laundry detergent? There's a good chance it has enzymes from companies like Novozymes that let you wash your clothes in cold water. Think of all the energy that saves, one load at a time.
So, okay, with all these amazing success stories, it begs the question, right? If this stuff is so great, why isn't everything made this way? Well, the biggest roadblock might not be what you think. It could actually be an education gap.
Check this out. A recent survey of chemistry professors found something really interesting. Almost all of them, like 87%, knew all about catalysis. That's a core concept. But when asked about life cycle impacts, thinking about a chemical's entire journey from creation to disposal, less than half were familiar with it. That's a pretty big hole in what's being taught.
And this isn't just some, academic trivia. This gap has real consequences. It directly affects what gets taught. So if the teachers aren't fully up to speed on these big sustainability ideas, then the new chemists they're training, well, they're heading into the world without all the tools they're going to need.
And when you ask the professors what the biggest roadblock is, it's not what you'd expect. It's not a lack of money or fancy equipment. Nope. The number one reason they gave was time. Just finding a way to cram this new information into a curriculum that's already jam-packed. It really comes down to a question of what we prioritize.
And wow, this awareness gap gets even bigger. The survey found that a whopping 86% of these chemistry teachers had never even heard of the Planetary Boundaries Framework. And nearly half hadn't heard of the UN's Sustainable Development Goals. I mean, these are two of the most important blueprints we have for a sustainable future. It just shows how deep this disconnect can be.
So that leaves us with a real paradox, doesn't it? We've got the science. We've got the tools. We know green chemistry has the potential to help solve some of our biggest environmental problems. But if the people who are supposed to be teaching the next generation of chemists don't have all the information themselves, how do we ever get there? It leaves us with a really critical question. If chemistry is so central to a sustainable future, how do we make sure its teachers have all the tools they need? Because figuring that out, well, that might be the most important chemical reaction we need to trigger.